There are still several things that fall under the umbrella of doing integrals without integration, so I will briefly talk through all the ideas, and you could click the link in the description if you want to learn more. In the end, I will have a summary for all the things we have gone through. Firstly, since we have computed some definite integrals without integration, through some simple algebraic manipulation, we can obtain the related indefinite integrals using the fundamental theorem of calculus. Here, since a is a constant, the negative f of a is a constant as well, so we can substitute it with c, just another constant, and this is the familiar form of the indefinite integral. So this is a formula to use to convert a definite integral into an indefinite one. Using this formula does not perform the action of integration at all, because the proof of the fundamental theorem of calculus does not use integration itself. You can ponder on this not so rigorous proof on the screen or check out the link in the description if you want some refreshing on this proof. Then there comes the formula Cavalieri derived. Cavalieri showed this for positive integers n up to 9, which can be generalized to all natural numbers. Although it was not originally Cavalieri's idea, we can derive this formula based on only some elementary results. For every rectangular strip as you see in Riemann sums, the length consists of gx and f of x, and since we have distributive law in multiplication, we can see this formula intuitively. Now consider another case where the function is stretched in the y direction by a factor of c, and the length of each rectangular strip is then stretched by a factor of c. Then due to the associativity of multiplication, we have this formula as well. Apart from stretching in the y direction, we can also stretch in the x direction. But remember that when we stretch by a factor of c, we changed from f of cx to f of x, not the other way around. In this case, the rectangular strip stretches by a factor of c in the x direction, so we have this formula as well. This result can be obtained by substitution, but what we have done is to simply stretch the area in the x direction. We can also translate the area to the left or right without the area changed, but remember that when we add c in the argument, the graph shifts to the left by c units, so we have this formula. Finally, we have this additive property of the definite integral, which you can see pretty easily in this diagram, as well as the obvious conclusion of the integral of 1. And with these intuitive properties of the definite integrals, we can already derive the Cavalieris quadrature formula. Firstly, we use the third property, which leads us to this expression. Then now we can use the second property of stretching in the y direction. And we have this. This integral is only dependent on n, and we call this expression a with subscript n. Due to the last property, a0 is equal to 1. Based on this property, we obtain this result. Since we have an to be this integral, as well as the result derived just a moment ago, we can rearrange as such. To obtain the same integral, we can also use the fourth property, which means this. Now we consider the c term in both expressions, which can be done using binomial theorem. We have this result, which means an is 1 over n plus 1. Since we previously obtained this result, the Cavalieris quadrature formula follows. The last one is a much more advanced tool than integration itself, but technically we do not consider any antiderivatives, so it also falls under the umbrella of this series. The residue theorem in complex analysis can be drastically simplified like this. Firstly, we extend the domain of the function to a complex plane. Then integrating a function from a to b can be visually represented as an arrow on the real axis from a to b. But what the residue theorem cares is a closed path, so you need to head back to where you started. One meaningful way is to walk around a semicircle. Let's say at this particular point inside this path, the function is undefined, and so we say there is a pole. If we now call the closed path gamma, the poles A0, A1, etc., then the residue theorem tells us that the integral along gamma is only dependent on the function behavior in the neighborhood of the poles. One way to use the residue theorem in normal integration for upper and lower limits to be the two infinities is to consider this semicircular path centered at the origin. Then we let a tend to infinity. We can then break the path into two sections. One is the straight line segment, the other is the semicircular arc. In some lucky situations, the arc section of the integral tends to 0 when a tends to infinity. The left side can then be calculated using the residue theorem, while the straight line path is just the integral we have been looking for. There could be other paths to take depending on the position of the poles as well as the lower and upper limits of your integral. This tool is especially useful if you are to calculate the integrals of rational functions. Of course, you don't have to understand all these, but a rough idea about what we are doing. It is just another tool we can use for integrals without integration. In fact, we can also do some types of indefinite integrals using complex analysis through some clever substitution and a bit more work. If you want more details, since you might have already known the residue theorem, feel free to check the link in the description. Throughout this video series, we have discussed quite a lot of methods to do integrals without using antiderivatives. In the beginning, we talked about Riemann sums with assistance from geometry or algebra. Then there is a method of exhaustion used by Archimedes, as well as the circular motion in physics to help us derive the integral, typically solved by integration by substitution. Just in this video, we have also discussed the Cavalieris quadrature formula derived using some basic properties of integrals that can be visualized using diagrams, as well as complex analysis, albeit not in detail. What this series shows is that there is not only one way to achieve the same task, and sometimes if you consider some other methods to solve the problem, you will have some more insights. Thanks for watching this video series. If you made it this far, make sure to subscribe if you haven't already, like and share this video. See you on the next video. Bye!